Hi everyone, I am Latarani HM, Assistant Professor of Mathematics, Government First Grade College, KR Nagara. Today concept is analytic function. Analytic function means a function to be a analytic. Consider a function f of z for the complex variable z and also consider center point z0. This function f of z is a differentiable not only at the center point z0, it also differentiable at all the points of z0, means neighborhood points of the z0. Then we can say that f of z is analytic. See the definition. A function f of z of the complex variable z is a analytic at a point z0 if its derivative exists not only at center point z0 but at each point, means at each point z in some neighborhood of z0. These analytic functions are also known as regular function and holomorphic function. Means we have this analytic function can also be called as other name, that is regular function or holomorphic function. And a function f of z is analytic at all every point of z0, at all every point of neighborhood point of the z0, and it is not a differentiable, means it is not a analytic at the center point. That is called as singular point or singularity of the function. So this is the definition for the singularity. What is the definition? If a function f of z, function of z, fails to be analytic. Analytic means differentiable. Fails to be analytic at a center point z0. Then this z0 is called singular point or singularity of the function or isolated singularity of the function. Means ಇಲ್ಲೆಲ್ಲ ಕಡೆನೂ ಡಿಫ್ರೆನ್ಷಿಯಬಲ್ ಆಗಿ ಈ ಸೆಂಟರ್ ಪಾಯಿಂಟಲ್ಲಿ ಮಾತ್ರ ಡಿಫ್ರೆನ್ಷಿಯೇಷನ್ ಎಕ್ಸಿಸ್ಟ್ ಆಗಲಿಲ್ಲ ಅಂದರೆ ದಟ್ ಪಾಯಿಂಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಸಿಂಗ್ಯುಲರ್ point or singularity of the function. Necessary and sufficient condition for f of z to be analytic. A function f of z is to be analytic, it satisfies the two conditions. One is necessary condition and sufficient condition. Now we discuss about the necessary condition for f of z to be analytic. What is the necessary condition for f of z is analytic? So this is the necessary condition for f of z to be a analytic. See here, what is this condition? This condition is nothing but CR equation. A f of z is satisfies the CR equation, then this f of z is to be a analytic. So theorem, if a function f of z is equal to u plus iv, u is a function of x and y and v is a function of x and y, is analytic in domain D. The partial derivatives are represented as del u by del x, del u by del y, del v by del x, del v by del y. Because u is a function of x and y, v is also function of x and y, therefore we take only partial derivatives because we have the two independent variables. The del u by del x can also be expressed like that, u suffix x. This is called as del v by del x. So this is del u by del y. This one is del v by del y. If the partial derivative should exist and satisfies the equation, this equation is also called as CR equation. CR equation means ux is equal to vy and uy is equal to minus vx. That is del u by del x is equal to del v by del y and del u by del y is equal to minus del v by del x. Proof. What is the given data here? The given data is the function f of z is analytic. F of z is analytic means what? Analytic means differentiation is exist according to the definition of differentiable. See here, by the data f of z is analytic in a domain D. Then analytic and differentiation is exist According to definition of differentiation, f dash z is equal to, we know the true differentiability formula. For this theorem, we can use this formula. F dash z is equal to limit delta z tends to 0, f of z plus delta z minus f of z whole divided by delta z, treated as equation number 1. Differentiation is exist and is unique irrespective path in which delta z tends to 0. Irrespective path means here we have the two paths. One is delta x tends to 0, another one is delta y tends to 0. Consider f of z is equal to u plus iv, and for this actual function, we are adding some increment, some changes. Increment means we are change the z in terms of z plus delta z. Here delta represent the small changes or small increment. Okay, f of z plus delta z. If z changes to z plus delta z, automatically x changes to x plus delta x and y changes to y plus delta y. Therefore, this equation can be written as f of z plus delta z is equal to u x plus delta x comma y plus delta y plus I into v x plus delta x comma y plus delta y. Here z is equal to what? Complex variable, that is x plus iy. Then delta z can be written as delta x plus I into delta y. Now consider equation number 1. For this equation number 1, we substitute f of z plus delta z value and also f of z value. We substitute f of z plus delta z and f of z and delta z, we get this equation. Now for this, delta z tends to 0 means we have the two paths along x-axis. Real axis represent x-axis and another one is along imaginary. Imaginary means y-axis. Now consider case 1. Let delta z tends to 0 along x-axis. Then delta y is equal to what? In x-axis, delta y is 0, delta z tends to delta x. Now substitute this value in above equation. Then f dash z is equal to limit delta x tends to 0, u x plus delta x y plus 0, that is y, plus I into v x plus delta x y plus delta y. Here plus delta y is in a 0, that is y, minus u of x comma y plus I into v x comma y whole divided by delta x plus this value is a 0, then we get only delta x. Now separate real part and imaginary part. We get f dash z is equal to limit delta x tends to 0, u x plus delta x comma y is a real part and another real part is here minus of u x comma y plus imaginary part I times v x plus delta x comma y minus v minus, sorry, here not plus, this is a minus sign, minus v x comma y. Then limit delta x tends to 0, u x plus delta x comma y minus u of x comma y whole divided by delta x plus I times limit delta x tends to 0, v x plus delta x comma y. This is not plus sign, we have to write this one as minus v of x comma y whole divided by delta x. Means we are applying the limit for real part and also imaginary part. So here this can be written as, we can write this one in terms of partial derivatives because u changes with respect to x, because here x plus delta x, delta represent the changes, small changes. Hence this can be written as del u by del x. Del u by del x means the partial derivative of u with respect to x, because here y is a constant, y not changes. Therefore we can treat this as a partial derivative of u with respect to x plus I into, this is the function of v changes with respect to which variable? X. Hence we can write dou v by dou x, treated as equation number 2. Now let us consider delta z tends to 0 along the y-axis. In y-axis we can put delta x is equal to what? 0 and delta z becomes I into delta y. Substitute these values in this equation. Therefore, f dash z is equal to limit delta y tends to 0, u x plus delta. Delta x is 0, so we get x only. Y plus delta y plus iv x comma y plus delta y minus of u x comma y plus I into v x comma y whole divided by delta x is a 0, remaining is I into delta y. Now, separate real part and imaginary part, we get like that. Then apply the limit for the real part and limit for the imaginary part. We obtain limit delta y tends to 0, u of x comma y plus delta y minus u of x comma y whole divided by denominator. What is the denominator? I into delta y plus limit delta y tends to 0, I into v of x comma y plus delta y comma v of x comma y whole divided by I into delta y. Here 1 by I is in a constant, take outside, then this can be written as the changes of u with respect to which variable? Y. Therefore, we express in terms of partial derivatives del u by del y, dou u by dou y plus limit delta y tends to 0. Here I get cancelled, remaining is v x comma y plus delta y minus v x comma y whole divided by delta y. Again, this represents the derivative of v with respect to y, derivative of v. That derivative should be partial because x does not change us, here changes only the y variable, therefore dou v by dou y. Treated this one as the equation number 3. From 2 and 3, LHS is same because LHS in the equation number 2 is f dash z and the equation number 3 also LHS is f dash z. Therefore, if LHS are same, then we are equating the RHS of 2 and 3. The RHS of equation 2 is dou u by dou x plus I into dou v by dou x, which is equal to the RHS of equation 3 is 1 by I dou u by dou y plus dou v by dou y. Now comparing the real part and imaginary part. What is the real part? See here, wait. Before taking comparison, first we take 1 by I to the numerator. See here, write dou u by dou x plus I into dou v by dou x as it is, and here take I to the numerator. When we shift numerator, we get minus I because I square is in a multiply and divide by numerator and denominator by I, then denominator becomes minus 1, numerator is in a I, that is minus I dou u by dou y plus dou v by dou y. Now comparing the real part and imaginary part. The real part of LHS is a dou u by dou x, which is equal to real part of RHS is dou v by dou y, and imaginary part. What is the imaginary part in LHS? Dou v by dou x is equal to dou u by dou y. This is called as the necessary condition for the analytic equation. A function f of z to be analytic, then it satisfies these two equations. That equations are called as a CR equation or Cauchy-Riemann equation. Okay. Then we move on to the sufficient condition. The second condition for the function f of z to be analytic. What is the sufficient condition? The sufficient condition is the four partial derivatives should be exist, and also it is a differentiable. U and V are the differentiable and satisfies the CR equation. So theorem is the function f of z is equal to u plus iv is a analytic in a domain D if first one is the four partial derivatives del u by del x, dou u by dou y plus dou v by dou x and dou v by dou y exist and are all the continuous in domain D. And second one is the u and v are a differentiable. U and v are being differentiable in the domain D and satisfies CR equation. CR equations means what? This is the CR equation. Del u by del x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. See here, if we prove the second condition, then no need to prove the first condition, because we know in the previous classes all differentiable function should be a continuous. So if you prove this second condition, need not to prove the first condition. Proof by the data, by given data, f of the condition 1 and 2 holds for the function f of z in the domain D. Now, by mean value theorem of a differential calculus, assume the Taylor series theorem for the two variables x and y. What is the Taylor series theorem? U of x plus delta x comma y plus delta y is equal to u x comma y plus dou u by dou x into delta x plus dou u by dou y into delta y plus second order derivatives and so on. Here delta represent the small changes. Delta square, delta cube, again it will be very small. Therefore we are neglecting the second and third or higher order terms. Therefore we consider only up to the first order terms. And v can be expressed x plus delta x comma y plus delta y is equal to v x comma y plus dou v by dou x into delta x plus dou v by dou y into delta y plus so on. Here we are neglecting the higher order derivatives because it is a very small. Therefore this above equation can be written as u x plus delta x comma y plus delta y, take u this side, we get minus u of x comma y is equal to dou u by dou x into delta x plus dou u by dou y into delta y, and second equation can be written as v of x plus delta x comma y plus delta y minus v of x comma y is equal to dou v by dou x into delta x plus dou v by dou y into delta y. Now consider f of z plus delta z minus f of z. Consider this function. Then substitute the value of f of z plus delta z and f of z. What is f of z plus delta z? We know that f of z is a u plus iv and f of z plus delta z means the small changes in x and also y. That is u of x plus delta x comma y plus delta y plus I into v x plus delta x comma y plus delta y minus of f of z value is u of x comma y plus I into v of x comma y. Now separate real part and imaginary part. So this is the real part plus imaginary part is I into v of x plus delta x comma y plus delta y minus v of x comma y. Now see here, this can be written as u of x plus delta x comma y plus delta y minus u of x comma y. This can be written as dou u by dou x into delta x plus dou u by dou y into delta y, because u changes both x variable and also y variable. That's why this can be written as dou u by dou x into delta x plus dou u by dou y into delta y plus I into, similarly here v changes to x variable and also v changes to y variable. By using the partial derivatives to total derivative, this can be written as dou v by dou x into delta x plus dou v by dou y into delta y. Now separate delta x terms and delta y terms. What are the delta x terms here? Delta x terms are dou u by dou x. Here delta x terms are I times dou v by dou x. So dou u by dou x plus I into dou v by dou x into delta x plus, now write the delta y function. Delta y function is dou u by dou y plus I into dou v by dou y. Now these bracket functions are same. Then we take the common term dou u by dou x plus I into dou v by dou x. Bracket function is not same. Therefore we have to make this bracket function as same by using the CR equation. What is the CR equation? Dou u by dou y can be written as minus dou v by dou x, and dou v by dou y can be written as dou u by dou x. By using CR equation, the second bracket function can be written as dou u by dou y is a minus dou v by dou x plus I into dou v by dou y can be written as dou u by dou x. Now, dou u by dou x plus I into dou v by dou x into delta x plus minus of dou v by dou x plus I into dou u by dou x into delta y. Because here the first bracket function in terms of the u and v is differentiate with respect to which variable? X variable. The second bracket function u and v differentiable with respect to which function? Y function. Now we have to make all the bracket function will be differentiate with respect to only x variable. Now by using CR equation, these all terms are u and v are differentiate with respect to which one? X variable. Therefore, the second term, this can be written as, here we take I as a common term, then we get dou u by dou x plus I. Here we have a minus 1. Minus 1 can be written as I square. Here we take one I as outside, then remaining is I into dou v by dou x. Now here these two are common. Same. These two are same. Therefore we take this function as a common. Dou u by dou x plus I into dou v by dou x into delta x plus I into delta y. What is delta x plus I into delta y? Delta x plus I into delta y is nothing but delta z. Now shift this delta z into the left side. We get f of z plus delta z minus f of z whole divided by f of z is equal to dou u by dou x plus I into dou v by dou x. Now apply the limiting on both sides. We get limit delta z tends to 0, f of z plus delta z minus f of z whole divided by delta z is equal to dou u by dou x plus I into dou v by dou x. Now this can be written as, now this shows the differentiability definition. Therefore this can be written as f dash z. F dash z is equal to dou u by dou x plus I into dou v by dou x. Now this shows the formula of the f dash z in the analytic function. Here f dash z can be written as u and v can be differentiate with respect to x variable. This one is also can be written as with respect to y variable. What is the formula? How to write this dou u by dou x and dou v by dou x in terms of y? By using the CR equation. What is the dou u by dou x? Dou u by dou x is in a dou v by dou y. And what is dou v by dou x? Minus dou u by dou y. This can also be expressed in terms of f dash z is equal to dou v by dou y minus I dou u by dou y. Now this represents the differentiable formula for the analytic function. Therefore differentiation is exists as the partial derivatives exist in the domain D. If differentiation is exist, then f of z is a analytic in domain D. Hence this is the sufficient condition for the analytic function. What is the sufficient condition for the analytic function? Means a function f of z to be analytic, then its sufficient condition is f dash z is exist. What is f dash z? F dash z means analytical function here. F dash z is equal to dou u by dou x plus I into dou v by dou x. Otherwise another formula is f dash z is equal to dou v by dou y minus I dou u by dou y. This is the proof of the sufficient condition for the analytic function. So here we have the two conditions for function f of z to be analytic. One is necessary condition. Necessary condition means the f of z is analytic, then it satisfies the CR equation. That is the necessary condition. What is the sufficient condition? A function f of z to be analytic, then f dash z is exist. That f dash z is nothing but dou u by dou x plus I into dou v by dou x, or another formula is f dash z is equal to dou v by dou y minus I into dou u by dou y. These two conditions are very useful in the solving the problems. Now we move on to the problems. First problem, verify Cauchy's-Riemann equation f of z is equal to z square. Verify Cauchy's-Riemann equation means we have to satisfy the CR equation. Let us consider f of z is equal to z square. What is z? Z is in a x plus iy. Apply a plus b whole square formula. After applying formula, we get x square minus y square plus I into 2xy. What is the real part? U is a x square minus y square. And what is v? 2xy. First we have to consider real part and imaginary part. And CR equation means we have the partial derivatives of u and v with respect to which variables? X and y. So differentiate u and v partially with respect to x. Differentiate partially means treat others are constant. Which is the other variable here? Y. So we have to treat y as a constant. Differentiation of u with respect to x can be written as ux is equal to differentiation of x square is 2x minus differentiation of y square is 0. And similarly, v with respect to x is dou v by dou x is equal to 2 into y is a constant, differentiation of x is 1. Therefore, answer is 2y. Now, differentiate u and v with respect to which variable? Y variable. Therefore, dou u by dou y can also be written as uy is equal to minus 2y and dou v by dou y is equal to 2 into x, which are constants. So, 2x into differentiation of y is 1. So, answer is 2x. Now, see here, ux is same as vy and uy is same as the minus of 2y minus of vx, otherwise vx is a minus of uy. Hence, we see that ux means del u by del x is equal to del v by del y and del u by del y is equal to minus del v by del x. Hence, CR equations are satisfied or CR equations are verified. This is the second problem. This one is same as the first problem. You have to try this problem. Then we goes to the another problem. What is the another problem? Show that f of z is equal to e power z is analytic and find f dash z. So ನಾವಿಲ್ಲಿ e power z ಅನ್ನ ಅನಾಲಿಟಿಕ್ ಅಂತಲೂ ತೋರಿಸಬೇಕು, ಜೊತೆಗೆ f dash z ಕೂಡ ಕಂಡುಹಿಡಿಯಬೇಕಾಗುತ್ತೆ. ಸೊ ಹಾಗಾಗಿ ನಾವು ಈ ಪ್ರಾಬ್ಲಮ್ಗೆ necessary condition ಯೂಸ್ ಮಾಡ್ತೀವಿ, sufficient condition ಯೂಸ್ ಮಾಡ್ತೀವಿ. What is the necessary condition? The necessary condition is CR equation is satisfied. The sufficient condition is f dash z is equal to ಏನಿದೆ f dash z ಏನಂತ ಬರೀತೀವಿ? dou u by dou x plus I into dou v by dou x. This is the formula of the sufficient condition. So ಈ ಪ್ರಾಬ್ಲಮ್ಗೆ ನಾವು ಎರಡು ಕಂಡೀಷನ್ಸ್ನ ಯೂಸ್ ಮಾಡ್ಕೋತೀವಿ. So see here solution. F of z is equal to, consider f of z. What is f of z? E power z. Here z is in a x plus iy. Now e power x plus iy can be written as e power x into e power iy. Here we are using the Euler's formula. What is Euler's formula for e to the power of iy? Cos y plus I sin y. Now separate real part and imaginary part. And what is the real part? U is equal to e power x cos y. What is the imaginary part for v? V is equal to e power x into sin y. Now differentiate u and v with respect to x and y partially. First differentiate with respect to x. Differentiation of u with respect to x is ux is equal to cos y constant, write as it is. Differentiation of e power x is e power x itself. And differentiation of v with respect to x is vx is equal to sin y is in a constant, write as it is. Differentiation of e power x is e power x. And now differentiate with respect to y. Differentiation of u with respect to y is uy is equal to e to the power of x. Differentiation of cos y is what? Minus sin y. And differentiation of v with respect to y is vy, which is equal to, write e power x as it is because it is in a constant. And differentiation of sin y is in a cos y. Now see here, ux is equal to what? Vy. Ux is equal to vy and uy is equal to minus vx or vx is equal to minus uy. Therefore, ux is equal to, we see that ux is equal to vy and uy is equal to minus vx. Hence, CR equations are satisfied. If CR equations are satisfied, Hence, the function f of z to be a analytic. Then we find f dash z. Means we write the formula. What is the formula for f dash z? F dash z is equal to, here f dash z means differentiation, but we are not write the differentiability formula, because here we have to show that f of z is analytic. Therefore, we are using the sufficient condition of the analytic function. The condition is f dash z is equal to dou u by dou x plus I into dou v by dou x. What is dou u by dou x? Dou u by dou x is e to the power of x into cos y, and dou v by dou x is e to the power of x into sin y. Substitute here. E to the power of x cos y plus I into e to the power of x into sin y. Here e power x is in a common function. Take outside. Remaining is cos y plus I sin y. By Euler's formula, this can be written as e to the power of iy. That is e to the power of x plus iy. Hence, f dash z is equal to e power z. See here. F of z is equal to e power z. Now, simple again, what is the differentiation of e power z andre ಏನಂತ ಹೇಳ್ತಾ ಇದ್ದೋ? e power z itself ಅಂತ ಹೇಳ್ತಾ ಇದ್ದೋ. ಬಟ್ ಇಲ್ಲಿ ನಾವು ಅನಾಲಿಟಿಕ್ ಫಂಕ್ಷನ್ ಯೂಸ್ ಮಾಡಿಕೊಂಡು ಸಾಲ್ವ್ ಮಾಡಿದ್ದೀವಿ. ಅಲ್ಲಿಯೂ ಕೂಡ ನಮಗೆ ಸೇಮ್ ವ್ಯಾಲ್ಯೂ ಬಂದಿದೆ. ದಟ್ ಈಸ್ ಎಫ್ ಡ್ಯಾಶ್ ಝೆಡ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಇ ಪವರ್ ಝೆಡ್. ಸೊ ದಿಸ್ ಈಸ್ the necessary and sufficient condition of the analytic function. Now we move on to the fourth one. Show that f of z is equal to cos z is an analytic, and hence find f dash z. So f of z is equal to cos z means what is the differentiation of cos? Minus sin. So by using analytic condition, we have to find the f dash z here. Answer: consider f of z is equal to cos z, where z is x plus iy. By using the compound angle formula, cos of a plus b formula. What is cos of a plus b formula? Cos a sin b, cos a cos b minus sin a sin b. Here cos iy can be expressed in terms of cos hyperbolic y, sin iy can be written as I into sin hyperbolic y. Now we are separate real part and imaginary part. Consider u is equal to cos x cos hy, and imaginary part v is equal to minus sin x sin hy. Now differentiate u and v with respect to x and also y. Differentiation of u with respect to x is ux is equal to cos hy is in a constant, right as it is. Differentiation of cos x is minus sin x. And vx is equal to sin hy constant, right as it is, minus differentiation of sin x is what? Cos x. Similarly, uy, means differentiation of u and v with respect to y is uy is equal to cos x. Differentiation of cos hyperbolic y is sin hyperbolic y, and this is not vx, this is vy. Vy is equal to minus sin x. Differentiation of sin hyperbolic y is cos hyperbolic y. So here this is not vx, it is a vy. Now see here, we've seen ux is equal to uy and vx is equal to minus of uy. Hence CR equations are satisfied. Therefore f of z is a analytic. If f of z is an analytic, then f dash is exist. When given function to be analytic, then differentiation is exist. Then what is the differentiation formula? Differentiation formula f dash z is equal to dou u by dou x plus I into dou v by dou x. What is dou u by dou x is minus sin x cos hyperbolic y plus I into what is dou v by dou x minus cos x sin hyperbolic y. So minus is in a common, take outside. Minus sin x cos iy, hyperbolic can be written as cos iy. Again plus I sin hyperbolic can be written as sin iy, cos x into sin yy. Minus here sin a cos b plus cos a sin b. This can be written as sin of a plus b. A is in x plus b is in a iy. Therefore minus sin of x plus iy. What is x plus iy? X plus iy is nothing but z. Hence f dash z is equal to minus sin z. So these two problems are also same as the previous problem. And another problem is verify whether f of z is equal to z minus z bar is a differentiable or not by using CR equation. Here we have to check the given function is a differentiable or not. Let us consider the given function. What is the given function? F of z is equal to z minus z bar. Substitute the z value. Z value is x plus iy and its conjugate is x minus iy. Simplify, we get x plus iy minus x plus iy, we get 2 into iy. Here real part is 0. Therefore u is equal to 0 and what is v? V is equal to 2y. V is equal to 2y. Now differentiate this with respect to x and also y. Differentiation of u with respect to x is 0. Differentiation of u with respect to y is 0. Similarly, differentiation of v with respect to x is in a 0. Differentiation of v with respect to y is in a 2. Now, we see that here ux not equal to vy. Ux is 0. What is vy? Vy is in a 2. One of the CR equation condition is not satisfied. Hence, CR equation are not satisfied. If CR equation is not satisfied, given function is not a analytic. Therefore, f of z is not a analytic. If f of z is not analytic, hence it is not a differentiable. Therefore, given function f of z is equal to z minus z bar is not a differentiable. Thank you.